Hello again, students. So, there's one last thing that I want to do with inverse trig functions. I want to think about to what extent do trig functions and inverse trig functions undo each other. Because the idea of inverse functions is that they should, right? If you take f of f inverse of x, or f inverse of f of x, you should always get x back. But remember, cosine inverse isn't literally the inverse to cosine. It's the inverse to cosine after you restrict its domain. So let's see what happens. Let's just be careful about it. So let's compute the cosine of the inverse cosine of 1/2. Well, I know what the inverse cosine of 1/2 is. I can use this lookup table. There's an input of 1/2. I want inverse cosine of 1/2. That's pi over 3. So that means that the cosine of the inverse cosine of 1/2 is the same thing as the cosine of pi over 3, because this input is literally the same as pi over 3. All I'm doing is evaluating from the inside out. And I know what the cosine of pi over 3 is. Where's my unit circle? There it is. An angle of pi over 3, I want cosine, so I get 1/2. Oh, well, we got the same thing out as we put in. And in fact, maybe you'll think that maybe there's a pattern here. Let's see it again. The sine of the inverse sine of -1. What's the inverse sine of -1? Well, -1 inverse sine negative pi over 2. And what's the sine of negative pi over 2? Well, looking at that unit circle, it's -1. In fact, there's something that's going to be true in general. Right, what do I know about, let's think just about cosine. If I take cosine inverse of some number, x, this is an angle in 0, pi, right, that's the range of inverse cosine, with cosine of that angle, call it theta, equal to x. Wait, so that means that this thing is the angle theta. So that means that cosine of the inverse cosine of x, well, that is the cosine of this angle theta, but I know what cosine of theta is. It's x. In fact, in general, cosine of cosine inverse of x is always equal to x, and the sine of sine inverse of x is always equal to x, with one important condition, provided that x happens to be in -1 to 1. And let's see what happens if you don't have that. Let's try to compute the sine of the inverse sine of 34. Well, let's, again, read from the inside out. So sine inverse of 34 is an angle whose sine is 34. So that means that it's some angle theta, so that when you rotate by it, I scrolled over so you could see the unit circle, so that you rotate by this angle, you will get a y value of 34. But no matter how many times you spin around, you only see y values between -1 and 1. You will never see an angle of 34. So there's an issue here. No such angle exists. So sine inverse of 34 does not exist. And you can't take the sine of something that doesn't exist. So the sine of the inverse sine of 34 does not exist. So that highlighted condition in the statement theorem 3 is very important. Let's try to, so what does this theorem say? Theorem 3 says that trig function of inverse trig function, those undo each other as long as your input is reasonable. Let's see if inverse trig function of trig function undo each other by, again, evaluating from the inside out. Let's try to compute the cosine, inverse cosine of the cosine of 3 pi. And, well, here, let's do it. So, let's see, an angle of 3 pi. Well, there's 1 pi, 2 pi, 3 pi. I land at an x value of -1. So cosine of 3 pi is -1. So this is the inverse cosine of the cosine of -1. Sorry, the inverse cosine of the cosine of 3 pi is the same as the inverse cosine of -1. And now by using this handy lookup table, the cosine of -1 is pi. Are these two the exact same? They are not. How about the second one? The inverse sine of the sine of 5 pi over 3. So I'll do the same thing. I'll evaluate it from the inside out. Let's compute the sine of 5 pi over 3. That's literally an angle that we see here, so that is negative root 3 over 2. Negative root 3 over 2. That is the sine of 5 pi over 3. Now I need to compute the inverse sine of negative root 3 over 2. Well, negative root 3 over 2, inverse sine is negative pi over 3. Interesting. So it looks like inverse sine and sine need not always be the same. And using a computer, let's actually see that they won't always be the same. I'm going to pause for a moment. Let's grab graphs of inverse sine of the sine of theta and the inverse cosine of the cosine of theta. I'll let theta run from negative 2 pi to 2 pi, but we can go even farther than that. Let's pause and come back in a moment. Or rather, I'll pause. You should just keep on watching. No, you should go to your own computer graphing tool and find these same graphs. Do that. All right, we are back. So we see in blue the graph of inverse cosine of cosine, and let's see, I only wanted it to go from negative 2 pi to 2 pi, so that will give me that much of the graph. But notice in general, it looks like you see this sawtooth pattern repeating. The graph of the inverse sine of the sine of x is the red one. So you see a very similar pattern, just shifted, I guess, down and to the left a little bit, or down and to the right. There's some periodicity that you can take advantage of. But here's the point. Are each of those graphs exactly the same as the graph of y equals x? They're not. Not the same as just y equals x. So there you can literally see really well, is sine of x, is the inverse sine of the sine of input always the same as the sine of that input? Nope. So I guess I've been saying x, I may as well change the variable name to x. It doesn't matter what the variable name is. So here are the graphs of the inverse sine of the sine of x and the inverse cosine of the cosine of x. So the inverse cosine of the cosine of x, let's make sure I get it right, has this sawtooth pattern, where here's the point 0, 0. There is the point pi, 0. Down here we see 2 pi, 0. And I guess if we go out one more, this will be 4 pi, 0. Oh, not pi, 0. But pi, pi. If we go backwards, then, well, you see that this looks like it's pretty even. So negative pi, pi. Down here we see negative 2 pi, 0. There's the graph of the inverse cosine of the cosine. Similarly, if we want the graph of inverse sine of sine, it still goes to the point 0, 0. I agree that this axis should be shifted some. It probably will be in the version that I put online. Up here we see the point pi over 2, pi over 2. Down to the point negative pi over 2, pi over 2. And then we see the same zigzag pattern. So 3 pi over 2, negative pi over 2, up to 2 pi, 0. And then the same sort of pattern going backwards. Nice. So we see that there's some complicated, fairly nice periodic behavior in the graph of inverse trig function evaluated at trig function. And what will happen by the end of this recording is I'll give you an algorithm to compute things like, well, inverse trig function evaluated at trig function. So, how should you think about inverse trig functions? You should think about the inverse sine of y as starting with the y coordinate you want to see and determining what rotation produces that y coordinate with the constraint that what's the range of inverse sine? Well, it's negative pi over 2 to pi over 2, so you're only allowed to use angles between negative pi over 2 and positive pi over 2. Similarly, you should think about inverse cosine as, well, I'm going to write a lot of similar words, as starting with an x-coordinate you want to see and determining what rotation between, well, what's the range of inverse cosine? It's 0 and pi. So the output of inverse cosine should be somewhere between 0 and pi produces this x value. So that means inverse sine, I'm allowed to use y values between negative pi over 2 and pi over 2. So what are the y, what, well, on the unit circle, those angles correspond to this piece of the unit circle. So when someone asks you to find the inverse sine of a number, they are asking you for an angle which lies apparently in quadrant 1 or quadrant 4, which has that y value. Similarly, if someone asks you for the inverse cosine of something, they're asking for an angle which produces that x value, and that angle has to live somewhere between 0 and pi, that is, in quadrant 1 or quadrant 3. So, summarizing, saying arcsine of y equals theta means that theta is an angle which is in either quadrant 1 or quadrant 4, which satisfies the equation sine theta equals y. If someone says arc cosine of x is equal to theta, then they're looking for an angle in either quadrant 1 or quadrant, oh, that's not quadrant 3, that's quadrant 2, or quadrant 2, which satisfies the equation cosine of theta equals x. So now let's go back to this point that I said I was going to come back to. How do you compute the inverse sine of the sine of alpha? Well, let's read that in terms of the stuff above. So this is saying that I want an angle, theta, in quadrant 1 or quadrant 4 with the y value of sine of alpha. So here's a general algorithm to do that. So I see one initial candidate. Certainly, rotation by alpha gives the right y value. That's good. But that angle alpha might not be in the right quadrant. It might be too big. It might be off by some 2 pi's. So we need to fix alpha. But alpha may not be in negative pi over 2 to pi over 2. So here's the plan. So first figure out what quadrant your angle lives in and throw out any excess 2 pi's. If your angle is in one of the forbidden quadrants, and in the case of sine, I guess that's quadrant 2 is forbidden, quadrant 3 is forbidden. If you're in a forbidden quadrant, then reflect over the y-axis to get an angle that is good. What does reflection over the y-axis do? So reflection over the y-axis replaces theta by pi minus theta. That'll give you an angle, and now just make sure it's in the right range. So there's the plan. Let's use that plan to do some computations. Let's try to compute the inverse sine of the sine of 71 pi over 7. So step 1, let's get rid of the excess 2 pi's. So I'll take 71 pi over 7, I'll re-express it so that I see the extra 2 pi's, and then I'll throw them out. So that should be a 71, not a 61. You could also do this with 61 pi over 6, but I'll do the one that's actually written above. Yeah, that's not really readable. (71 pi over 7). So writing this, well, I know how to divide 71 by 7. That will give me 10 pi plus an extra pi over 7. So, where are some extra 2 pi's? There are a whole bunch of extra 2 pi's right there, right? 10 pi is 5 copies of 2 pi. That's 5 full revolutions. Those don't change the sign of this value. So the second... so I guess this would be like the first guess is 71 pi over 7, but it's too big. It's not in between negative pi over 2 and pi over 2. So the second guess will just be pi over 7. So, next, let's check if that angle is in a forbidden quadrant. Let's do it by drawing a picture of this angle. So an angle of pi over 7 is that angle. Right? Rotate forward by a very small amount. It's in quadrant 1. Quadrant 1 is fine. Is this number between negative pi over 2 and pi over 2? It is, right? Pi over 7 is already between negative pi over 2 and pi over 2. So that means the inverse sine of the sine of 71 pi over 7 is pi over 7. And maybe just for emphasis, you can use a machine to help you with some of these computations. I'll go do that and bring it back. Alright, here we are. So I just used the Google calculator and computed that the arc sine of the sine of 71 pi over 7 is 0.45 radians approximately, but that's kind of hard to tell if that's the same thing as pi over 7, right? So in order to determine if it is, I guess one way is just remember that decimal approximation. That's the same decimal approximation. Good. So I think that I believe that they are actually equal. Let's go back to the task at hand and do another computation. By hand again. Let's try to compute the inverse sine of the sine of 33 pi over 7. So step 1, let's get rid of some extra 2 pi's. So, I don't know, maybe I'll start by just reminding you how to do long division. So I want to know how many times I'll do this off to the side to compute how many times 7 goes into negative 33. So it'll be negative. 7 goes into 33 4 times. So I'll subtract 28, leaving me with, oh goodness, a remainder of 5. So what does that mean? That means negative 33 pi over 7 is the same thing as negative 4 pi minus 5 pi over 7. Maybe instead you did the same division and you got negative 5 pi plus 2 pi over 7. Both reasonable things to write down. I'll use the top one. So, do I see any excess 2 pi's? I do. I see negative 4 pi. That is negative 2 full revolutions. Negative 2 full revolutions won't change anything. So, as my second guess, I will use negative 5 pi over 7. Is this angle in a forbidden quadrant? If so, I will do some reflection. Well, let's draw an angle of negative 5 pi over 7. Let's draw it right here. So that means I want to rotate negative 5 pi radians in the negative direction. So I'll go this way. This is only pi over 2, and that's like 3.5 pi over 7, so I need to go farther. I don't want to go all the way over to the x-axis though. So it's an angle, it's in here. That's in quadrant 2. That's bad. So in order to get a second guess, I'll take that guess and I'll reflect it over the x-axis. Nope, reflect that over the y-axis. So to reflect over the y-axis and see what we get. Boop-a-doop-a-doop-a-doo. So in order to reflect over the y-axis, I'll need to take pi minus the angle I already had. Pi minus negative 5 pi over 7. What do I wind up with? Well, let's do that. That'll be the same thing as pi plus 5 pi over 7, and I wrote the pi the way I did because the first thing I'm going to do is I'm going to get a common denominator by, instead of dividing pi, I'll write 7 pi over 7. Well, 7 plus 5 is 12 pi over 7. And let's think about what angle that would correspond to. So that angle would correspond to, so starting there and rotating forward by pi over 2, 2 pi over 2, 3 pi over 2, so 3 pi over 2, well, let's see, that's like, there's 7 pi over 7, 8 pi over 7, 9 pi over 7, 10 pi over 7, 11, 12, 13 pi over 7, so that's like this angle. Okay, so it's at least in the right quadrant now. That's good. But tell me, is 12 pi over 7 between negative pi over 2 and pi over 2? It's not. 12 pi over 7 is too big. So to come up with a better guess, I should go 12 pi over 7, and I can subtract off some full revolutions. Let's subtract off 2 pi. If you saw an angle that was like really, really big, then maybe you could be more systematic than this, but I'll just subtract out a single 2 pi. That'll give me 12 pi over 7 minus 14 pi over 7, leaving me with negative 2 pi over 7. So the inverse sine of the sine of negative 33 pi over 7 is negative 2 pi over 7. Wonderful. Well, again, let's go back and just do some computer-aided computations. Let's see if it actually agrees. I'll pause. You do this at the same time as I do it, and then we'll come back together. Alright, here we are. This time I'm using the Wolfram Alpha calculator just in order to demo that you have other tools at your disposal. You have your own handheld graphing calculators, for example. The arc sine of the sine of negative 33 pi over 7. Here it is in pretty print, so I can check that I've actually entered what I think I wanted to answer. I think that's the same. Gives me an answer of negative 2 pi over 7. So we're in good shape. So the last thing that I want to do is I want to do something very similar, but for cosine instead. Let's try to compute the cosine inverse of the cosine of any angle, and we'll follow really similar steps. If I want to compute the inverse cosine of the cosine of 71 pi over 7, so first I'll rewrite 71 pi over 7 so that I see some excess 2 pi's that I can throw out. So the initial guess would be like 71 pi over 7. But you can see automatically that that is definitely not between 0 and pi. So I'll throw out all the extra 2 pi's that I can. So just like before, you would rewrite that as 10 pi plus pi over 7. And so that would give you a second guess of pi over 7. Is this angle in a forbidden quadrant? Well, let's draw a picture. An angle of pi over 7 puts us like there. That's in quadrant 1. We're fine. Quadrant 1 is fine. So our current guess is pi over 7. Is that between 0 and pi? It is, right? It's positive and it's really, really small. Really, really small is an overstatement, but it's definitely less than pi. So that means the inverse cosine of the cosine of 71 pi over 7 is pi over 7. Let's do the same thing for an example involving sine. Let's compute, nope, another angle, still cosine. Let's compute the inverse cosine of the cosine of negative 34 pi over 7. So step 1, re-express so that you see all of the, some excess 2 pi's, and work it out from there. So I won't include the negative sign this time. I think that just confused the analysis before. 34 pi over 7. So what's a multiple of 7 that I know that's a little bit less than 34? Well, 28 will do. That's not how you do division, Chris. So 28 will do, and that's 7 times 4. Doing the subtraction, we get 6, so the remainder is 6. So that's 4 and 6 sevenths. So that means that negative 34 pi over 7 is the same thing as negative 4 pi over 7 minus an extra 6 pi over 7. So, I must be getting tired. I'm doing everything wrong. Of course, how is that different from any other day, right? So, throwing out the extra 2 pi's, this is an even multiple of pi. So that just corresponds to negative 2 full revolutions. That doesn't even change the value of cosine. So it can't change the value of the inverse cosine of the cosine. So, as my second guess, I will return negative 6 pi over 7. So, let's draw a picture. So an angle of negative 6 pi over 7, that's almost negative pi, right? So it's like an angle like that is in quadrant 3. And remember, the acceptable outputs for inverse cosine are quadrant 1 or quadrant 2. This is not in those two quadrants. So let's think about what reflection we want to do. So I'll have to write something, right here. So if your angle is in one of the forbidden quadrants, then I want to do a reflection that preserves the x value, because the x value is cosine. So I want to do a reflection over not the y-axis, but the x-axis. So let's reflect over the x-axis. So that corresponds to replacing the angle theta with negative theta. So the next guess will be, so I guess this is the third guess, will be negative 6 pi over 7, also known as just 6 pi over 7. And now you ask yourself, is 6 pi over 7 between 0 and pi? It is, right? It's bigger than 0. And it's less than 7 pi over 7. So the inverse sine of the sine of negative 34 pi over 7 is 6 pi over 7. Great. I'll get this uploading, and I'll talk to you again real soon.